Hello everyone. My name is Wennan Shi. Today I would like to share my project denoising gravitational wave signals from cold-collapsed supernova using deep learning. My supervisor is Matthew Edwards, and he thanks for his guidance and support for this project. In 1905, Einstein predicted the existence of gravitational waves in his general theory of relativity. It was not until a century later that humans directly observed a GW from the merge of two black holes for the first time. At present, humans have observed GW events several times from the merge of compact binary systems. However, another significant source, GWs from cold-collapsed supernovae, has not yet been observed. In addition to GW detection, since noise complicates the process of detection and analysis, reducing noise interference and improving detect sensitivities are also the important topics. Currently, Rover and Edwards et al. Proposed a Bayesian principal component regression method to denoise cold-collapsed GW signals. This method depends on noise power spectral density, which required a solid background in astrophysics. There have been no deep learning approaches to denoise GW signals for cold-collapsed supernovae. So we proposed using the denoising autoencoder method to denoise cold-collapsed GW signals. Our project will focus on these three research questions. The method can effectively extract cold-collapsed GW signals from noisy data, and it is expected to achieve better denoising results than the existing Bayesian PCR method. The method also do not require a calculation of the noise PSD. The original data come from numerical general relativistic hydrodynamic simulations. In our project, we use processed data from Edwards, comprising around 1,800 cold-collapsed signals, each with a length of 226. We randomly split the data set into train, validation, and the test set in 70-50-50 ratio. The noise simulation is a quite complicated task. We just simplify the work of Rover et al. To generate colored stationary Gaussian noise by ourselves. We consider the noise PSD as a non-parameter and derive the standard deviation of the Fourier frequencies. Then, sample from the Gaussian distribution with standard deviation at zero mean. We perform an inverse Fourier transform on the noise in the frequency domain to obtain the noise in the time domain. First, we reproduce the Bayesian PCR method and use it as a baseline. We perform PCA on the training set and extract the first 20 principal components. These components are considered as explanatory variables of the linear model. The linear model in the frequency domain just should like this. Here, y tilde is a Fourier transfer noise data. Alpha is the regression coefficients vector. Epsilon tilde is the Fourier transfer colored noise vector. The likelihood function comes from the Edwards et al. In their work. We assume a uniform prior on the principal components coefficients. The posterior distribution is a multivariate Gaussian with a parameter mu and sigma. So we can directly sample the principal component coefficients alpha from the posterior. When constructing the signals, we take the linear combination of the principal components and the posterior samples of alpha and compute the pointwise mean. About the denoising autoencoder, the figure shows our DAE model structure. We built two layers, one-dimension convolutional layers in the encode, as well as two one-dimensional transposed convolutional layers in the decoder. We use the period rule as an active function because it can automatically just adjust the negative slope during training. There are a lot of hyperparameters in the deep learning model. Due to the time limitations, we in this project we just adjust the kernel size as 19. We also incorporate the L1 regularization to prevent overfittings. The figure shows the training loss curves. We can see after 200 epochs, both training loss and validation loss showed a significant decrease and trend to stabilize, indicating that the model has converged. We also did robustness validations. The figure shows the waveform of the same signal injected with the different scale noise. Then we can see after 5 times of the noise level, the shape of the original signal becomes indistinguishable. We directly apply both trained models to the noisy data and compare the MSE at different noise scales. We also retrain the DAE model, but without changing the hyperparameters with noise data of different scales. The results show that our DAE model performs significantly better than the PCR. The validation and test losses are only 30% of those of the PCR method. However, the DAE training is quite time consuming, with a duration of roughly around 27 times that of the PCR. About robustness verification, when we directly apply both trained models to data with different noise levels, the MSE of the DAE model, we can see the blue curve increase more dramatically, indicating that the significant decline in performance at higher noise scales. But if we retrain the DAE model with different noise scales, it exhibits a slow increase in MSE and maintains a relatively low level, as shown in the green curves in the figure, demonstrating the exceptional robustness. So we compare the denoising performance. The MSE of the DAE model is only 30% of that obtained using the PCR method, and the retrained DAE model shows the excellent robustness. So we recommend the DAE method if the task focuses on the denoising results. However, the training time of DAE is about 27 times that of a PCR. In contrast, Bayesian PCR does not require the large-scale data to improve generalization capability. On the limited computing costs, Bayesian PCR is a superior choice. About interpretability, DAE introduces numerous randomness during training, such as a random weight initialization and stochastic gradient descent. But the Bayesian framework allows for the interpretation by deriving statistical measures from the posterior distribution. Therefore, Bayesian PCR is a favorite by scientists. The PCR model relies on the noise PSD, which lacks an adaptive mechanism, while the AE model does not require the PSD-related knowledge. It can adapt to any type of noise data. Therefore, in terms of scalability, the DAE model offers unparalleled advantages. We're encouraged by the powerful denoising capability of the DAE model. As a deep learning model, the DAE model has many hyperparameters that can be tuned. So we will further explore the impact of multiple hyperparameters on this on its performance. The color noise in this project as used is relatively simple. Further studies will incorporate more complex noise, such as non-Gaussian and non-linear noise, to further explore the denoising capabilities of the DAE model. Yeah, here's the reference. Thank you. Any questions?
So in practice, how often do you think this needs to be retrained? So you talked about that the training is quite complex, 27 times more than standard before. So how often does it require retraining?
Yeah, the DAE model as a deep learning model is quite time consuming. Yeah. Yes, retrain. When we test the robustness, I spend a lot of time to retrain the model, just because the original model just learned some information from the normal noise, but don't have any information about the scaled noise. Yeah, so we just use the different data set to retrain our DAE model. Yeah, quite time consuming. Yeah.
What does DAE stand for?
Denoising autoencoder. Denoising autoencoder. Autoencode. Just show the first. Just a moment. The last one. Denoising autoencoder. Yeah.
So what are your plans now?
Plans now?
Career-wise?
Yeah, job hunting. Yeah.
Within New Zealand?
Yeah. Still in progress. Yeah.
Okay, thank you.
Yeah, thank you.